There are many different kinds of mass spectrometry that measure any number of things about a sample, but they all have similar basic components. First, the sample is injected into the spectrophotometer. There has to be a source that can give a particle a positive electrical charge. This is referred to as an ionization source. When we're studying isotopes, the particles in question are either atoms, which is the case for most of our elements, or small polyatomic molecules, which is the case for the 7 diatomic and the handful of polyatomic elements. The beam of ionized particles is narrowed down through a series of lenses. The particles need to be charged as their response to being in an electrical field is being measured by the instrument. Particles that are smaller in mass will be easier to manipulate in the field and will move further than the larger particles. The particles travel from this magnetic field onto the detector through a mass analyzer, where they are sorted by size. On the other end of the mass analyzer is the detector, which quantifies the separated particles. The detector presents data in terms of the mass to charge ratio of the particles, and you'll often see this on the x-axis of a mass spectrum. This ratio relates particles' mass to its electrical charge. Since all of our particles will have a similar charge, and since the only two subatomic particles that have any mass associated with them are the protons and the neutrons, the mass to charge ratio really sorts our particles by mass number. Either of these would be applicable as a label for the x-axis, though you will most often see the mass to charge ratio. The detector helps to count how many particles have a given mass and reports that as a relative abundance, which can be found on the y-axis of our spectrum. The abundance is just a percentage, and as such, the relative abundance is really a part over a whole. The part is the number of particles of a certain isotope, and the whole is the total number of particles of all of our isotopes. The peaks produced by the detector are often thin, straight, vertical lines, similar to these. Each isotope will have its own peak, and those peaks will correspond to the mass number of that isotope. In the case of boron, shown here, those mass numbers are 10 and 11 AMU. The height of the peak corresponds to the percent abundance of our isotopes. In the case of boron, boron 11 is highly prevalent with an abundance of over 80%, and boron 10 is much less prevalent and has an abundance that's about a quarter of boron 11's. While you will not be responsible for collecting data on a mass spec, you will need to be able to retrieve key information from a graph similar to this one. Ensure that you can identify the mass numbers for the isotopes, in this case boron 10 and boron 11, as well as the percent abundances for each isotope. Know that in this case, the percent abundances are given right above the peak, and lots of times they will be. But you may also need to use values given on the y-axis to get a good guess at an abundance. Additional questions you should be prepared for include identifying the total number of isotopes. Remember, each isotope gets its own peak, so this is as simple as counting peaks. Any identified peak will count, even if the percent abundance labeled is quite small. The heights of the peaks will differ from graph to graph as the percent abundances change from element to element. One very important skill is to review a mass spectrum and make a good first guess of the average atomic mass for an element. In the case of boron, I know that the average atomic mass will not be lower than 10, as there are not peaks to the left of that boron 10 peak. I also know that the average atomic mass cannot be higher than 11, as there are no peaks to the right of my boron 11 peak. So whatever I come up with has to be between 10 and 11 AMU. Since more than 80% of my sample has a mass of 11 AMU, the calculated value will be skewed heavily towards 11 AMU. But the 20% of boron 10 in my sample is significant enough that I won't get all the way to 11, while still being small enough to ensure that my value won't get too much below 10.5 either. So I can say that the average atomic mass is most likely somewhere between 10.6 and probably 10.9 AMU. If I didn't already know this was boron, I could turn to the periodic table and identify the element with an average atomic mass closest to these parameters. Indeed, boron has an average atomic mass of 10.81 AMU, which is fairly close to my guesstimate.